Hello and welcome to another episode of Enough with the Science. I'm Joe.
And I am Senan, and this week Joe is back here to face another storm of invective from me.
A storm of invective. Very nicely done. Nice. I see what you did there. Yes, this is part 2 of a two-parter. So it probably the last part
Well,
then
it
of
couldn't,
a
it couldn't
series.
really be part 2 of a one-parter now, could it?
Well, it could be part 2 of a three-parter.
Correct, yeah, but
Yeah.
anyway.
And the way you are talking today, this could be a three-parter, but we're going to make it a two-parter. We're going to get through all this information because we had like a great reaction to last week's show on the atmosphere. And
So last week we covered a bit of the atmosphere and we ran out of time. So this is part 2 of our deep dive into the atmosphere.
it is a big atmosphere.
It is a big atmosphere. It's a big topic. Yeah.
Yeah.
There's a lot happening up there.
So do you want to run over what we covered last week, just in case
very,
somebody forgot?
Very briefly, we spoke about why do we even have an atmosphere? Why does planet Earth have air? Mars doesn't really have any. Well, 2 key features. Earth has a lot of gravity and that pulls the air down like a blanket around the planet and holds it locked in around us. And the other thing is we have a molten iron core in the center of the Earth that's moving. Moving iron generates a magnetic field.
There's a third reason.
That magnetic field, well, let me finish the second reason for God's sake, would you? Moving iron generates a magnetic field, and that is like a blanket protecting us from the solar wind, which otherwise would strip away our atmosphere gradually.
That was very good. Sorry, I did jump in there because you covered it in great detail last week, and I remembered everything you said, so I didn't think we needed to do that again. So,
and the third reason is,
because otherwise we wouldn't be able to make this podcast.
Well, that would you think? Yeah, the universe actually wants this podcast so badly that it just spontaneously provided us with an
I can't see why not. I can't see why not.
Billions of years of evolution, just so you and I could reach the pinnacle of planet Earth's evolution.
Absolutely. Well, I wouldn't say we're the pinnacle. I would say we're somewhere along the road, but not the pinnacle.
Anyway. We also spoke last week about what are the ingredients of our atmosphere. 78% of it is nitrogen gas in the form of N2. It's mostly inert, which means that it doesn't really react much with anything but we will find out later today that it does actually play a role. 21% is oxygen. Just the right amount. It's the Goldilocks amount. Too much oxygen, we would be poisoned and the Earth would be a firestorm, and not enough oxygen, you wouldn't be here. Then 1% is argon. Argon is just chilling out, ignoring everything and everybody. It doesn't do anything. It's just there in the atmosphere.
That must be nice.
Wouldn't it be lovely to be able to just do your own thing and not worry about anything else at all? Mind you, not very social, not very much of a sense of community.
Not interacting with anybody, nobody listening to your podcast.
Yeah. So effectively reality as it is now.
We're going to change our name to Argon. The Argon podcast.
Enough with the argon. Also, the several trace gases, tiny amounts. So, for example, carbon dioxide, which of course gets a lot of coverage in the press, is only 0.04 or 1/20th of 1% of the Earth's atmosphere. Various other things, water vapor, methane, ozone, and lots of other little bits and pieces. But those are the main ones. And then we also spoke last week briefly about the 5 layers. So these are going from the ground up. Humans, for their own convenience, have identified 5 layers just based around temperature. So these layers have different temperatures. And the lowest layer, the troposphere, is where we live. And it is also where the weather is. So it's the one that affects us most. Right, so what are we going to talk about this week?
Yes.
We're going to talk about the wind and the weather because
we're Irish.
We're Irish and we're pathologically programmed to talk about the wind and the weather.
To our interaction, our daily interaction with anybody is like talk about the wind and the weather.
I mean, we're famous for striking up conversations with complete strangers at the most inopportune times, and 9 times out of 10, it's about the weather.
But even like transactional conversations that if you have to ring somebody or like you're dealing with something in work and like there's always, and what's it like there? I'm good, enjoying the weather. They're like, it's always the precursor to getting anything done.
Yeah. And I mean, you and I swim in the sea and, we always start every conversation before we get into the water is, it's cold today, isn't it? Like we didn't expect that.
It's like a surprise every single day.
So we're going to talk about the wind and the weather. Greenhouse gas is a very hot topic because of global warming. You can see what I did there, didn't you?
Yeah, I wish you hadn't, but I could see it. I think like most people could see it from about 10 miles away.
Yeah. So we're going to talk about greenhouse gases and what they are and why they are. And we're even going to briefly touch on the opposite, which are things in the atmosphere that have cooled the planet sometimes. And we're going to finish up then with an electrifying topic, which is electricity in the atmosphere.
Well, you got electrifying and electricity into the same segue. It's like watching a master at work.
Right, global wind patterns. Let's talk about that.
Okay.
So wind is basically driven by uneven solar heating. So some parts of the Earth receive more sunshine than others.
You can say that again.
Down near the equator, the things get much hotter than they do up at the poles. And when the ground is warm, it heats the air up above it. So that heat from the ground radiates back out and heats the air up above it. And you then get a thing called convection. Essentially, hot air rises and cold air sinks. Mm-hmm. And that's the basic mechanism, with some added complication that we'll talk about in a minute, that drives the winds that make our weather.
So the hot air rises at the equator.
Rises at the equator, sinks at the poles.
And so it goes up and then it zips over and comes back down again. It's the same.
Pretty much, yeah. There's like a circular conveyor belt going on there. Now, it's a little bit more complicated than that, and we'll try and explain that. But let's go back to basics here. What is convection in the first place? Because it plays such an important role in
You have a very strong conviction about this.
I have a conviction about convection. So heat gives the molecules in the air more energy. So when those molecules heat up, what is actually happening to them is they're starting to move faster. That any molecule that gets hotter, what's really happening is it's now moving faster than it was when it was colder. So the molecules are now moving much faster and they're colliding with each other. Now, they always collide with each other. That's not unusual. But now that they're going faster, those collisions are much more violent, much more energetic, and they bounce off each other much faster than they used to. So they spread apart. They go further apart than they would normally be. There's more nothingness between them because of how their collisions are making them bounce further apart. And the result is that air which has been heated up is now less dense. What does less dense mean? It means take a cubic meter of that air, there are fewer molecules in the less dense air versus there is in cold, more dense air.
So colder air is denser.
Colder air is denser because the molecules have less energy to bounce off each other.
So I imagine intellectually I must be practically frozen.
You've now got a pocket of heated air that's less dense than the air that's around it that's cooler. So what happens? It floats up. That's what convection is. Or in the opposite case, in the poles, you've got a pocket of cold air that's colder, i.e. denser than the air around it, so it sinks. So that's essentially what's going on with convection. And you end up with pockets of high pressure and low pressure. So in the case of near the equator, close to the ground, underneath where that air rose up, is now lower pressure because some of the molecules drifted away upwards. Mm-hmm. And the opposite is happening up at the poles. Close to ground level, you've now got a pocket of higher pressure because air has sunk into one area. And as always happens in a gas that's at a high pressure, it tries to move towards an area of low pressure. So you get a wind flowing along the surface of the earth towards the low pressure area at the equator. The opposite is happening high in the atmosphere. The hot air that rose up into the atmosphere is now trying to flow towards the pocket of what was cold air near the poles that sunk and left a low pressure pocket in its wake. So you end up with this circular conveyor belt.
Okay, so basically like the wind or the air is moving at the ground level from the pole to the equator.
Yeah.
And higher up, it's moving from the equator to the pole.
Yeah. That's pretty much it, yeah. And if the Earth was not rotating, that's exactly what would be happening.
Okay.
Right? But
because the Earth is rotating.
The rotation of the Earth makes things much more complicated and adds a lot of chaos into the movement of air in our atmosphere. And of course, I should point out that movement of air is what we call the wind, right?
Yeah. Good. Thanks for pointing that out.
Wind is air trying to go from an area of high pressure to an area of low pressure. That's all it is. So what happens is the Earth is rotating pretty fast and it bends that air as it's flowing. So you end up with what's called the Coriolis effect, where the air that's trying to flow from high pressure to low pressure is getting bent to one side or the other.
Okay. Because of the rotation.
Because of the rotation of the Earth. Northern hemisphere one way, southern hemisphere the other way. The rotation is so strong that it breaks up the cell that would normally... So normally if the Earth wasn't rotating, you would have a single conveyor belt going from the pole down to the equator and back again. Right?
Yes.
That gets broken up by the strength of the rotation of the Earth into three separate circular conveyor belts. So if you like, about 1/3 of the way up from the equator towards the pole, there's one. In that lower third, if you like, close to the equator. Then you've got the middle section where we in Ireland live, where that middle third between the pole and the equator is got another circulating area, and then up towards the North Pole there's a third one. And they're rotating in different directions, of course, as luck would have it.
Of course they are. Of course.
And that results in what's known as the trade winds. So if you sail a boat down close to the equator, reliably there's a wind that flows from east to west, because the trade wind caused by that conveyor belt that's near the equator is causing the ground winds to flow from east to west, right?
Okay.
If you come up here to where we live in Ireland, which is roughly halfway between the equator and the North Pole, okay, it's a bit closer to the North Pole, but we'll for the sake of simplicity, we'll say halfway. Here, the winds predominantly flow from west to east. Not always, but the most reliable, the winds generally speaking, flow from west to east. And so those are what are called the trade winds. And back in the day when international trade relied upon sailing ships, there was no engines in the ships, there was no airplanes. It was much more economically advantageous to find a route where you could take advantage of the trade winds. If you had a reliable wind that always blew you in a particular direction, then that was much cheaper and quicker way of sailing than trying to sail against the wind.
Okay.
Unfortunately, that led to
I knew you were going to go down here.
Yeah.
You couldn't just. I was like, he's going to leave it. Just call them the trade winds. That's it.
Our ancestors,
the atmosphere.
Our ancestors went down there, so unfortunately, I'm going to have to follow them. Despicable slave trade was essentially propped up by the trade winds, because you had the people from Western Europe, who at that time that was the most civilized, or civilized, that's questionable, advanced part of the world, and they sailed their sailing ships south until they got to the west coast of Africa, where there was the trade winds heading to the west. What did they do in the west coast of Africa but kidnap a lot of the locals who were not a lot less advanced and imprison them. Their boats then followed the trade winds along parallel to the equator until they got to the Americas, whereupon they sold those poor unfortunate individuals to some very unscrupulous people, and then used that money to buy natural resources from the New World, be it food or minerals or whatever useful things were coming from the Americas, and then they would sail a little bit north to pick up the trade winds coming back the other way towards back here, heading east towards us, and that's how they would come back here and sell their whatever ill-gotten goods they'd got in the Americas here in Europe.
And are you blaming the trade winds for this?
You would have to wonder if the slave trade would have happened at all if the trade winds had not been the way they were.
Wow. You are blaming the trade winds for this.
Yeah, well, look, let's not take the blame away from the people who actually perpetrated.
Man's inhumanity to man.
Yeah. But the trade winds played a part, unwittingly.
Right.
Yeah, so, and the trade winds, of course, are not only used by unscrupulous humans. Birds and insects that migrate over long distances will often make use of them as well. Because
I was hoping you're going to have examples of scrupulous humans. They're like, not only used by unscrupulous humans, some people use it to help people, but no. Birds and insects.
Well, an interesting little digression. Well, birds and insects, they have discovered through natural evolution that certain routes are easier for them. They're more likely to successfully reach somewhere if they go with the wind than if they go against it. So they tend to take advantage of the trade winds. I don't know if you've ever noticed that sometimes when you fly in a plane east-west and come back the same route a few days later or a week later or whatever, often it'll be much longer one way than it is the other way. And that's typically the effect of the trade winds speeding up the plane one way and slowing it down the other way. As I said, the rotation of the Earth makes the direction of our wind and our weather much more complicated because it bends the wind sideways. Mm-hmm. One other thing that makes adds an extra complication into the mix is ocean currents. So there are very long currents that flow persistently, reliably in certain patterns through the ocean. We're talking about currents that literally could go around the Earth. They're like, one of them is known as the AMOC, which has an influence in the North Atlantic where we live. Those currents are moving water from one place to another. So if they flow from a place that's warm to a place that's cold, they're bringing some warm water with them. And the effect is that they're slightly warming up that place that would otherwise not be quite so warm. And vice versa. They may be cooling down other places that wouldn't normally be so cold. And that affects convection in those areas. So it either adds to or subtracts from the convection that's going on in those areas. Very localized effect, but it adds to the confusion and chaos that's involved in our weather and trying to predict our wind patterns and so on.
Okay. So we benefit from that.
We don't especially benefit. Well, we benefit from it in terms of here in Ireland, we're at the same latitude as Newfoundland in Canada, but their weather is much colder than ours. So we have that ocean current that flows across the North Atlantic from the Gulf of Mexico, roughly speaking, brings warmth with it and keeps our winters mild. So yeah, we do benefit from it that way, but it does add to the chaos of how hard it is to predict our weather in terms of, is it going to be stormy tomorrow or not, or is it, which way is the wind going to blow tomorrow, and is there going to be much rain tomorrow, all that stuff. And on the subject of rain, we should probably move on to the water cycle, which is the other big thing that's going on in our atmosphere that affects us every day. And
in Ireland, every second, every 10 minutes.
Provides us with that fantastic phrase here in Ireland, it's a soft day, isn't it?
Yeah, that covers a multitude.
And for the uninitiated, that means it's raining. and not usually means it's raining and not terribly cold. Would I be right about that?
Well, yeah, it's soft, yeah, and it means it's not raining particularly heavily.
Yeah.
Sometimes soft can mean that it's actually raining, but it's not falling.
Yeah.
It's actually just sitting there.
Yeah, it's like
you just walk out and you get wet. You don't understand how it happens.
It's incessant.
Yeah.
It's not particularly heavy, but
Yeah.
it's gone on for the last 76 hours.
Yeah. It's
So
hard
let's
to see
talk
the
about
road.
how all that happens, right? Evaporation. So if convection is the great engine that drives the winds, evaporation is the great engine that drives the rain and the water cycle, and indeed the amount of water vapor that is in the atmosphere and acting as a greenhouse gas.
You're getting David Attenborough there. You're like kind of that, just that segue was it like if convection is the engine that drives the winds, then evaporation. Because that's one of the best.
There's a part of me wants to try and take.
That's wow. No, I just brought a bus there. I like that one.
Yeah, well. That was a happy accident. So what happens? Very similar to convection, heat energizes the water molecules. So normally water molecules, they're happily stuck to their peers, to their neighbors, and they form a liquid. Add some heat and you're adding extra energy to those water molecules, meaning they're starting to move faster, and that gives them, the ones at the surface then get enough energy to be able to jump away from their neighbors. So they're no longer glued onto their neighbors. They jump away and they become a water molecule drifting through the air. And that's essentially what evaporation is. So the more heat that the surface of the water has, the more evaporation takes place. Of course, when those water molecules jump away to become water vapor in the air, they take that extra energy with them. So water that's evaporating loses energy, begins to cool down a bit. We mentioned earlier on that we both do a bit of swimming. Your wetsuit on a windy day after you come out of the sea, you get cold quite quickly in your wet wetsuit, and that's because the water is evaporating off the surface of the suit and it is taking heat. That extra heat is going with it. So that's a very tangible demonstration of that principle. So what happens? That vapor, those individual water molecules are now drifting around in the air. They gradually drift up. Convection happens in the air. They drift up with the convection higher and higher into the clouds. And
so it's convection that brings them up.
Yeah.
The evaporation doesn't do. The evaporation just leaves them sitting where they are, and then the convection brings them.
Yeah, the evaporation just allows them to jump away from the surface of the water. Yeah. So convection or wind or some kind of disturbance in the air is moving them away up higher into the atmosphere. Of course, the higher they go, the colder they get, and a point comes where they can't stay as water vapor anymore, and they start to condense into tiny, tiny little droplets of liquid water. So they're moving from being a gas basically into being tiny droplets of liquid. And when they do that, the extra energy that they gained that allowed them to evaporate in the first place gets released into the air around them. So the condensation of water vapor to turn it into clouds actually warms up the air around that area. And that's a very significant driver of storms and hurricanes, because there is so much condensation of water vapor going on inside storms and hurricanes that extra heat that's being added into the center of the storm or the hurricane causes more convection, more movement of the air, strengthens the storm.
Right.
So it's a well-known effect of warmer oceans being caused by global warming, resulting in stronger storms, and that's why it's because there is more evaporation going on because the oceans are warmer, and that extra energy that's in that evaporated water vapor is getting released when it condenses again inside the clouds of the storm, and that heat causes more condensation to strengthen the storm.
If you believe that sort of thing.
If you believe that sort of thing, which unfortunately not all of our fellow human beings do, maybe they will after they've heard this.
Look it up.
And then, of course, eventually you've got rain or snow or hailstones or some kind of precipitation. So how does that happen? So initially, when that water vapor condenses back into tiny little droplets, they're so small, they're not heavy enough to fall. The movement in the air is enough to keep them up there. They're so light. But gradually they start to clump together and form bigger droplets, or if it's a cold air, depending on how cold the air is, they might form directly into ice crystals. But they reach a point where they're big enough that they're heavy now, and the air movement, natural movement of the air can't keep them up anymore, and they fall, and that's essentially how rain happens.
It's not the sky crying.
It's not the sky crying, much as you might have believed when you were a young whippersnapper.
Until just before this podcast.
You're still a young whippersnapper. Okay, greenhouse gases. Let's talk about that big
Happy.
demon.
Yes, the happy topic.
That big demon that is warming the planet for us. Now, the important thing to understand about greenhouse gases is they're not ultimately evil. We actually need them. There's a right amount of greenhouse gases that we should have.
I don't think gas can be evil. Can they get there's no intent. Gas doesn't have intent.
Well, does evil require intent?
I would imagine it does, yeah.
Okay, that's a
you can't
philosophical
It
question.
can't be accidentally evil.
Okay, enough with the philosophy, back to the science. So we need the right amount. If there was no greenhouse gases at all, the Earth would be a ball of ice. It would be roughly 33 degrees colder than it is now, which is enough for the entire planet to be in an ice age. So yeah, we need the right amount. What do greenhouse gases do? Well, they have an interesting property. So the surface of the Earth is warm, and like any other body that's warm, it emits infrared radiation. That is more or less the definition of what being warm is. And that infrared radiation travels upwards, heading towards space, but then it meets a greenhouse gas, which absorbs it and then re-emits it back downwards. It's a bit like a mirror. It's not exactly the same as a mirror, but it's the end result is like as if the greenhouse gas is a mirror for infrared.
But so if this so there's a molecule of whatever greenhouse gas, CO2 or whatever it is.
Yeah.
And it takes in the UV.
No, infrared.
Infrared. Takes in
Yes.
the infrared, sorry. Yeah. Hands up. Okay, takes in the infrared.
Yeah.
And then it re-emits it.
Yeah.
In only the same direction that it came from.
No, it probably re-emits some of it upwards, but enough of it is re-emitted back down to act as a kind of an insulator, as a blanket.
Yeah.
Okay. So it works kind of like a blanket. I mean, you put a blanket on top of you when you lie in the bed. Some of the heat from your body is still getting through that blanket out to the other side, but the blanket is keeping most of it in. So it's kind of like that. And there are several gases involved. Carbon dioxide, of course, is the main one that we all know about. And that's probably because it's one of the most common, and it's the one that human activity of burning stuff is releasing in large amounts into the atmosphere. But there's other ones, and some of them are in fact much more potent than the carbon dioxide is. Methane, another biologically produced gas.
Burps.
Comes from several sources, including cow burps, yes, because of the metabolism of the vegetation they've eaten in their stomach. But if you had a cubic meter of CO2 and a cubic meter of methane, the methane would be 25 to 80 times more potent as a greenhouse gas than the same amount of CO2. So it's a really potent gas. But the good news about it is that it degrades naturally over a period of about 10 years in the atmosphere. It turns slowly into carbon dioxide. So it becomes less potent as a greenhouse gas over time. So that's kind of good news. Produced from lots of interesting places, essentially anywhere that vegetation is decomposing in a damp environment. So, flooded wetlands, marshes.
So concrete them all. Concrete all the marshes.
Landfill dumps where we have dumped food waste, for example, or other kinds of biological waste.
Incinerate everything.
Yeah, incinerate everything. But the problem then is, of course, how much carbon dioxide are you going to release by incinerating everything?
I'm trying to be solution focused here.
I release that, yeah, but solutions that work are the ones we're after. Up near the northern Russia, northern Canada, northern Scandinavia, etc., there's an area of what's called permafrost, so it's permanently frozen ground. And trapped under that is pockets of methane that have been there for thousands or millions of years. Now, as the planet is gradually warming, those permafrost areas are starting to thaw, and the bubbles of reservoirs of methane that are trapped underneath them are starting to get released. So there's a bit of a feedback loop going on there with methane. As the planet gets warmer, more methane is getting released from these areas, which is going to make the planet warmer.
Feedback loops.
Feedback loops, yeah. And then there's termites. You think cow burps are bad.
Really, it's that like they're on the same level. They're more than cow burps.
Yeah. In the parts of the world where there are a lot of termites, like here in Ireland, I don't think there's hardly any termites.
Thankfully.
But places like Africa and Australia, there are huge populations of them, and they produce a significant amount of it.
From burps as well, is it?
Actually, I don't know what the mechanism with termites is.
Yeah.
So another one is nitrous oxide. Now, this one's really potent. Nitrous oxide, in comparison to carbon dioxide, 300 times more potent as a greenhouse gas. So 300 times better at reflecting infrared radiation back down onto the Earth.
Or worse. 300 times worse at reflecting.
Worse. Now that you mentioned it, worse would probably be. So where's that coming from? Well, our commercial fertilizers that we use in intensive agriculture all over the world are a big source of nitrous oxide. But also any machine that's burning, like cars that use diesel or petrol, aircraft, diesel generators, ships with big diesel engines, etc. They're all producing nitrous oxide as one of their waste products. So yeah, that's another source of human-driven global warming. And then we've, of course, got water vapor. In some parts of the planet, is by far the most abundant greenhouse gas. Places with high humidity, it could be as much as 4% of the atmosphere. But then in other parts, there's practically none of it. So the amount of it that's there varies widely. But there's another feedback loop, of course, with the water vapor, because the warmer the planet gets, the more water vapor is going to evaporate off the surface of the ocean, because that's more heat and gone into the ocean. And that means more water vapor in the atmosphere, meaning the planet gets warmer, meaning the oceans get warmer, meaning more evaporation, and there's a loop going on there too. So it's in terms of human-caused global warming, I mean, it's generally agreed that it began with the Industrial Revolution about 270 years ago in Northern Europe, primarily Britain. So if we were to tomorrow stop all of our industrial activity that burns it produces these greenhouse gases, so no more cars unless they're electric, or buses or trucks, no more airplanes or ships unless they're electric.
Gaviscon for cows.
Gaviscon for cows. Well, I don't think we can blame the cows for the Industrial Revolution.
Gaviscon.
There we are. Quick, copyright that one. Somebody will steal it. Anyway, if we were to basically put humanity back to where it was before the Industrial Revolution tomorrow, how long would it take for those greenhouse gases to return to the level they were at 270 years ago?
I want to say 270 years.
It's not as simple as that, although intuitively you would think that, but it's a question of how long does it take these gases to actually break down in the atmosphere. In the case of methane, as I said, 10 years, that's not so bad. Nitrous oxide, about 100 years before that dissipates. Carbon dioxide, however, at least 10,000 years, and could be as much as 100,000 years before it breaks down.
We're finished.
So, yeah.
We're finished. The game over.
I mean, global warming, the cat is out of the bag, the horse has bolted, and every other
Switch the lights off, folks.
Every other analogy you can think of. So all we can hope to do really is slow it down to the point where we have enough time to adapt to the changes it brings to the world.
Move. We'll have to move.
Well, I mean, it's not going to make the world entirely unlivable, just some parts of it. And we're going to have to change our agriculture practices, as well, because places that we can grow food in now, we might not be able to in the future. We might have to find new places like the ocean where we can generate food, etc. But so all we can do is hope to slow it down by moving away from any process that's creating more of these gases, and then that gives us a chance to take our time and adjust our civilization to cope with it.
There you go. There's a happy thought for today. We can't fix it, but we can learn to live with it.
But we should talk about, seeing as we've talking about gases in the atmosphere that warm up the planet, we should talk about other ones that cool it down.
Well, why don't we just make more of them gases?
Well, they have toxic effects that we mightn't like too much.
You don't want to listen to any of my suggestions today.
Well, look, I would prefer if you brought forward well-researched suggestions. They are toxic, but in small amounts in the atmosphere, we can cope with them just about. They basically act like a mirror in the opposite direction. So they reflect sunlight back out into space. So these sulfur compounds, if they're in the air, some of the sunlight that comes in gets reflected off them and back out into space. Some of the most extreme examples have been big volcanic eruptions because there's a lot of sulfur in lava. So these sulfurous compounds in gas form get released alongside, the erupting lava in volcanoes. And there has been some pretty horrific examples. 1815, a volcano called Tambora erupted, and it was known as the year without a summer because globally temperatures were reduced by about 0.5 degree on average, but that's average over the whole globe. Some places like Europe, it was much more than 0.5 degree that the temperatures
Tambora was the name of the volcano.
Tambora was the name of the place where the volcano was, yeah. And for example, there was
They make
places...
tambourines there.
Very hot, runny ones, yes. There was places in June that had snow that would never, ever have snow at that time of the year. There was a lot of crop failures because, a lot of crops have evolved to expect temperatures to be at a certain level at certain times of the year. So when temperatures or the amount of available sunlight reduced as a result of the stuff that was in the air from this volcano, a lot of crops failed. A bit of a tenuous connection. It's theorized that Mary Shelley was inspired to write Frankenstein because that summer was so miserable that she didn't bother going outdoors to enjoy herself out in the sunlight.
So volcanic eruptions inspire literature.
Yeah, isn't it amazing the things that inspire creepy stories? Another one, 1783 in Iceland, the Laki fissure erupted. And, well, in Iceland itself, the toxic chemicals that came out of that volcano killed about 1/4 of the population and killed practically all the livestock, so a lot of them starved. But in Europe, it caused a huge amount of crop failures as well. Combination of the toxic chemicals and the fact that it was cold and not much sunlight. And it is theorized that it might have contributed to the French Revolution because a fairly discontented lower class population only needed a little bit more discontent, i.e. they had no food because their crops were failing, to push them into a revolutionary state of mind. So yeah, that's a
the
theory.
Butterfly effect.
The butterfly effect. If a volcano spouts in Iceland, then Marie Antoinette will lose her head a few months later. Right, electricity in the atmosphere. We're kind of running a bit tight on time now, so I'm gonna only talk about this briefly. So there's this thing called the global electric circuit, and basically the surface of the Earth is negatively charged, and the ionosphere, which is an area very high in the atmosphere, is positively charged. And this, it sounds extreme, like the potential difference between those two areas is about 250,000 volts. That's 250,000 volts. It sounds like an awful lot, but because it's spread out over such a huge area, it that isn't going to cause sparks spontaneously in the atmosphere. And
so we can't generate electricity from this.
Probably not, no. But it gradually dissipates, but it's kept topped up by lightning, which is a different animal altogether. So lightning, the voltages are much higher.
So just wait. So the lightning hits the ground and makes it negative.
Yeah, I guess, yeah, or either that or makes the ionosphere positive, one or the other, or both.
Right.
What lightning is an interesting mechanism. So thunderclouds are characterized by being very tall columns of cloud. And there's a huge amount of convection going on inside those clouds. And that accelerates ice crystals in the clouds up. So as the clouds grow into enormous pillars of grey, dark cloud, inside in them, ice crystals are shooting is probably the wrong word, but ice crystals are being accelerated upwards in through the cloud. And they carry a massive electrical charge with them as they move upwards.
From the bottom to the top.
From the bottom to the top. And you end up with literally 100 million volts of a difference in charge between the top of the cloud and the bottom. And normally air is an insulator. So air, you have two wires, one negative, one positive. You hold them an inch apart in the air and no electricity flows between them.
Yeah.
But air is only capable of, it's only so strong. So once you get a potential difference of 100 million volts in a cloud, it's enough to break down the insulation of the air. And the air actually turns into a circuit. And that's a lightning bolt that you see traveling from the ground up into the cloud.
From the ground up.
Yeah. Well, I've seen slow motion video that seems to indicate the lightning starts at the ground and makes its way up. I don't know if that's actually the case, to be honest with you, but it certainly appeared to me in the videos I've seen that that's what was happening. Yeah.
And do other people concur with this? Like, surely your nerd community, you have some sort of sites that you all converse about these things on, no?
Community is a word I don't understand. I'm a true nerd where community just doesn't happen.
So essentially, the lightning, because all the history, the gods are angry, the thunderbolts are raining down from the sky, the zigzag comes down from the clouds to the earth. But if you watch it in slow motion, it actually starts at the ground and pops back up to the cloud.
Yeah, so it seems, yeah.
That's bizarre.
But initially, if you look at it in real slow motion, you see these tendrils starting to extend down from the cloud, not the true lightning bolt, but like tenuous little tendrils that maybe are following simultaneously several paths, a bit like a root of a plant, if you've seen the soil washed off the root of a plant. And then one of them appears to make contact with the ground. And then you see this really bright bolt travel upwards through it from the ground.
So a tendril of something comes out of the cloud.
It's like as if there's like probe mini lightning bolts coming out of the cloud looking for a path to the ground. That's kind of what it looks like.
Okay, that's even scarier.
Yeah. And I mean, there's about 8 million lightning bolts a day worldwide. Can you believe it?
No.
It's amazing. That tells you the size of the planet. See, we here in Ireland don't get lightning very often, but they're, of course, in the tropics, they get it practically on a daily basis. So yeah, and those are replenishing that charge difference between the ionosphere and the surface of the Earth. But they're also doing an interesting thing. Plants need lightning. Because nitrates, which is a form of nitrogen, is one of the nutrients that plants need. And the nitrogen in our atmosphere is in N2 format, which is not a nitrate that plants can use. So
it's inert.
It's pretty much inert, and I'm glad you remember that word.
There we go. I am listening.
Anyway, what happens is the power of the lightning bolt hits some of that N2 in the atmosphere and what's called fixes it. It means it converts it into a nitrate that plants can use. So lightning bolts are actually creating the nitrates that plants can use. Now, there are also some bacteria that do it also, but a large proportion of it is done by lightning bolts.
So plants to be in trouble.
Plants to be in trouble if there was no lightning, yeah. So I think it's maybe time that we wrapped it up for this week. So it's goodbye from me, Senan, until the next time. And hey, if you have a minute and you really like the podcast, maybe leave us a bit of a review.
Listen, thanks for listening. Hope to catch you next time. Good luck.
Okay, goodbye.